Hello class, I hope you are all doing okay. I hope that you and your families are safe and you've stocked up on some yummy food to keep yourself occupied during this time. We are going to get started with our next unit, and it's the last unit of calculus, the last unit of new content. Also, I apologize in advance for the shadow. I can't seem to figure out a great setup. But we'll work around this. So anyways, Unit 9 is polar and parametric calculus. If for some reason you did not learn about polar equations or parametric equations in pre-calc honors, please pause this video, go back to the email I sent with the links to the Khan Academy videos about reviewing what these equations are, and check out the review worksheets that I sent out to just get your brains with what are parametric equations, what are polar equations, how to use the functions in different settings. So this is for those of you who feel confident in your polar and parametric knowledge, and now we're going to apply it to calculus. So the first thing really is like, what are these types of equations and why are they so important? So like, why would we use them? What are we going to do with them in calculus? We're going to differentiate them. We're going to find arc length of them. We will do calculus of vector valued functions, meaning using position vectors, velocity vectors, acceleration vectors, looking at different contexts, etc. We will also find area of polar graphs, tangent lines of polar graphs, and polar arc length. That's what we're going to do with calculus. And then why are they so important and where do we see this in real life? Anything really with GPS uses polar and parametric. So if you are thinking about writing an app and you want your user's location, it's going to involve parametric equations. And also, the higher up you go in math, the more you're going to see how polar and parametric equations connect to all sorts of job fields, not just coding or physics, but things in medicine and game design and engineering as well. All right, so that's the why we're doing this. Now let's get into the new content. So I'm going to try to just shift this over, maybe avoid the shadow a little bit. Well, not for this video. Okay, sorry guys. So, differentiating parametric equations. That's the first thing that we're going to do. We've got a parametric equation, x of t and y of t. And the trick here is we want to differentiate this with respect to x, not t. We want the derivative dy dx. And what we have is x equals something in terms of t and y equals something in terms of t, where t is our independent variable. What we want is dy dx. So if you think about it right here, when this says x equals something in terms of t, we're talking x of t, and y in terms of t, y of t. So how can we go from differentiating this and differentiating this to get back to dy dx? So I'd encourage you to pause the video right now and try to think about a possible way to go from x of t and y of t to separate or seemingly separate functions to the derivative dy dx. So hopefully you've paused, and the big idea is we will differentiate both equations with respect to t and then divide dy dt by dx dt. The dt's are going to cancel like a fraction would, and we're left with dy dx. So what we mean here is we have x of t equals something, y of t equals something. We're going to take the derivative of x of t, dx dt. Don't ask me why I put parentheses on that. And then dy dt. You can't see that. Sorry, folks. And then we will, since we want dy over dx, we'll say dy dt divided by dx dt. And here is where these dt's are going to cancel out in quotations. And we're left with dy dx, our first derivative. So I'm going to pause for you to process for a minute. And there we go. That's how I can move this around. Okay. Thank you for being patient with me. If you have a question so far, jot it down. Come to office hours. Ask it during class time at our Zoom meeting. Okay, so we get that big idea. So dy dx is equal to the derivative of our y divided by the derivative of our x function. Okay, so what about the second derivative? The second derivative is a little bit more complicated in that we can't just take the derivative of this, because remember, the derivative of dy dx is actually going to be in terms of t. So what we're going to need to do is take the derivative of our derivative. That's what we're doing here. Derivative of the derivative with respect to t. And then we're going to divide it by the derivative. This is just the first derivative of x of t. And that will get us our second derivative. So those are two equations you do need to know. First, how to find the first derivative, and then second, how to find the second derivative of parametric equations. And what we're going to do next is an example. So take a pause, write down any questions if you have them yet. And let's move on to an example. So here our example says, x is equal to cosine of t and y is equal to 3 sine of t. Find dy dx and find the second derivative. Just a note that things are going to need to be clearly labeled so that whoever is reading your work, whether it be me or the AP reader, can follow it. And that sounds silly, but it is important. And with parametrics, this can get a little complicated because you're asked to find two different things. So first, let's do our first derivative. So dy dx, well, we need the derivative of our x component. So we're just going to look at the derivative of cosine, and that is negative sine of t. And we're going to look at the derivative of our y component, 3 sine of t, so that would just be 3 cosine of t. Then together, we are going to divide the derivative of our y component divided by the derivative of our x component to get dy dx. Ooh, I'm so sorry, guys. It's been a while since I've used this. 3 cosine of t, because that's dy dt, divided by negative sine of t. And you can leave your answer for the first derivative like this. You also can you also can simplify this to negative 3 cotangent of t. That works as well. In fact, this right here, this simplified version might actually be more useful because when we find the second derivative, so for d2, we're not going to have to do chain rule with, and sorry, by chain rule I mean quotient rule, with cosine divided by negative sine. Here we just need to know what is the derivative of cotangent. So let's mosey on over to the second derivative. Now that we've got the first part, so d2y dx squared. Well, we know we need to take the derivative of negative 3 cotangent of t with respect to t, and we will divide it by the derivative of our x component, negative sine of t. And now if we look at our help you sheet, we'll see that derivative of cotangent is cosecant squared. So we get 3 cosecant squared of t all over negative sine of t. And we can do some simplifying, but this is also fine. So that is how you're going to just attack solving for derivatives of parametric equations. Organizing your work, make sure things are labeled with dx, dt, dy, dt, whether it's the first derivative or the second. We do want to make that as organized as possible. So jot down a question you have about this example, save it for when we have virtual office hours or virtual class. And the next thing you're going to want to do is, you do not need to take 3.5 minutes exactly. Take whatever time you need to try these problems out, and pause the video, because in like 30 seconds I'm going to flash the answer key so that you can check your work. Answer key is coming in 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So go ahead and you can pause it now just to check your work later. And really, thanks for sticking in there. I'm going to try to adjust the camera settings and my little setup before I film the next video. So take some practice time, and I will see you on the next video in a bit.